Thank you so much, Amy. Yeah, it's very nice to be back to Hack in the Box after 7 years. Okay,
Yeah.
yeah.
Welcome back.
Okay, so today my talk's about a new assembler framework named Keystone. Actually, everything about Keystone, full source code, binary package, documentation, tutorials are already released long ago, and you can get everything at the website keystoneengine.org over there. Okay, so my name is Quynh, and I have some academic background. I work for NTU University in Singapore, and my research area is mainly on low-level stuff like operating system, virtual machine, or reversing. And I happen to be the founder and maintainer of three open source frameworks for reversing: Capstone disassembler, Unicorn emulator, and Keystone assembler. So that's a quick question. Anybody here use any of these frameworks? Okay, so yeah. Actually, I think you might indirectly use these frameworks because many reversing tools use them inside. Okay, so in this talk, I first introduce some background on assembler frameworks, and I show you many problems. And because those problems cannot be fixed, I came up with a new framework named Keystone. And I will present the ideas behind that, how I design and implemented it. And after that, I introduced a new tool named KeyPatch built on top of Keystone and conclusion. And yeah, if you have enough time, we have some more demos. Okay, so 2 years ago, in 2014, I presented a capstone, which is the only open source multi-architectures, multi-platform, multi-binding disassemblers in Black Hat US 2 years ago. Last year in Black Hat US, I introduced another work, which is a Unicorn CPU emulator. Okay, so now in 2016, we have some fundamental frameworks for a lot of reverse ring tools. And actually, there are a lot of tools already built on top of these frameworks. So given the binary, you can use capstone to reverse it into assembly. And after that, you can do a lot of uh, static analysis on top of the assembly. Or you can send the binary to emulator, so you can really understand uh, what the binary really does. So capstone, you can see that is for static analysis, and Unicorn emulator is for dynamic analysis. So the question is, what is still missing here? So look at the diagram again. You can see that we need binary to decode, to reverse, to assembly, right? We also need binary for emulator. So the question is, where to get the binary? So most of the time you get binary from somewhere, but sometimes you need to generate the binary yourself. So how to generate the binary yourself? Most of the time you need to compile the assembly to generate the binary. And the binary can be decoded again, or the binary can be sent to the emulator. So what is missing here is the assembler framework. So by definition, assembler is a tool that if you give it some assembly instruction, the tool in compiles assembly instruction and give you back the encoding of the instruction. So first of all, for x86, the Intel CPU, if you compile inc ex, the red instruction over there, it will give you the output which is 1 by 40. And if you run this 1 by 40 on the CPU, it will add on to ex registers. So the assembler, it might support high-level concepts like macros or functions. And here actually we want to emphasize on frameworks. We do not want the tool, but we want a framework which means allow you to build tools on top of that. So typically reversing tools can use assembler frameworks to dynamically compile code at runtime. And as output, you have a binary. And the binary can be used for binary matching or binary rewrite. Yeah, so those applications. So internally, all the assembler work in the same way. So if you give the assembler some assembly instructions, you need to pass the assembly into multiple statements. And after that, the assembler will compile each statement into the instructions. So you can see that for the last step to compile each instruction, the assembler need to understand how to compile code, input code to machine code, and you need to reference the CPU manual as this step. So now, if you want to you want to build a new assembler yourself, what you need to do? Too bad there are a lot of works. You need to have good understanding on the CPU encoding of every instruction set in the CPU. You need to know all the instruction inside CPU, which is a lot of works. Because for example, for Intel CPU, the latest edition has something like 1,600 instructions. So to support all of them is a lot of works. And the worst thing is that the CPU vendors, they frequently introduce new instructions. So you need to keep up with that. And it's not easy at all. So here's my definition for good assembler frameworks. First one is it must be a true framework, which means it should not, when you compile some assembly code, you should not call one external process to do that, but you had to do that everything inside internally. So you can embed your assembler inside your tool, and you do not need to depend on external process. A good assembler framework should support multiple architectures, not only Intel, but also ARM, x84, MIPS, PowerPC, Spark, and so on. It should have our own kind of platforms running on Windows, Linux, Mac, iOS, Android, and everything. And should be updated. It should support the latest instruction set of every CPU. And because usually people build tools not on low-level languages like C, they use high-level languages like Python or Ruby or JavaScript or Go. A good framework should support bindings, so you can build your tools using those high-level languages. Too bad. If you look at the existing assembler frameworks before Keystone, you can see there's nothing up to my standard. There's nothing good. So we have something like Yasmer, which only support Intel CPU and nothing else. But it's no longer updated. It has many technical issues. And yeah, it's actually not used by a lot of people. Intel has something named XED, which is standard tool for Intel architectures, Intel CPU. But this one is closed source. You cannot fix bugs. You cannot rely on Intel to fix bugs because you might report bugs to them, but they do not fix that. It's surprisingly, XED even is from Intel, made by Intel, but it missed many instructions. And you cannot do anything because it's closed source. And now if you want to have framework to support other architectures like ARM, ARM64, MIPS, PowerPC, Spark, and good luck, there's no such a thing. Okay, so without a reasonable assembler frameworks, people struggle for many years. It's never stopped. So typically, when you want to compile some assembly instruction in your tool, this is the typical way. You write each assembly instruction into a file, and you call assembler tool to compile that file. But the story is not over there. You, as output, you have only like object file, which is not a final output. You need to call a linker to link that object file to get the final executable. And finally, you need to write some special parser to parse the final executable file to get the final encoding, which is, you can see the many steps, which is tedious, ugly, and is not efficient at all. And you can see that you have very little control on the internal process on those steps. And cross platform support is very poor. So first of all, if you want to compile ARM instruction on Windows, then good luck. There's no such a thing. Okay, so I want a good assembler which should support own type architectures. It should be multi-platform, run on own type OS, Windows, Linux, Mac, iOS, Android, and so on. It should support the latest instruction sets on those CPUs. It should be independent, but have multiple bindings built on top of that. So the low-level framework can be built in C or C++, but they have bindings built on those low-level frameworks. So the issue that even in 2016 this year, there's just no reasonable things like that. So you can keep looking, but you don't find anything. And even worse, apparently nobody wants to fix the problem. So you can have this problem like forever, and nothing will work in the end. So the point is that if you sit down and wait for somebody to come to fix that for you, the wait may be forever. Because I had so much fun with Capstone framework, with Unicorn framework, so I decided to step up again and try to solve this problem. And that's why Keystone was built. So the name of Keystone came up from some private conversation with FX. So in architecture, Keystone is a piece of stone that you put on top of an arch during construction to lock on those other stone in their position. So because what you want to do is you want something that's the final missing piece in a set of reversing frameworks, right? So Keystone is like very suitable for the name. And also Keystone assembler would make a good couple with a Capstone disassembler. So Keystone is like a perfect name for my project. Okay, so I developed Keystone. I ran a quick Indiegogo campaign to raise some funding for 3 weeks, and I got a lot of interest. A lot of people contributed, and I know some of you are here. Thank you so much. The beta code was released in April, which has only Python binding at that time, and we ran a beta test for 1 month, and after 1 month, people have to build more bindings for Node.js, for Ruby, for Go, and for Rust. And the first version was released in May. The second stable version was released last month in July, and we have 2 more bindings in Haskell and Okemon. So all is good. Okay, so the thing is that I want to build Keystone, but you can see that there are huge amount of works. There's too many architectures I want to support. For each architecture, there are too many instructions. And finally, limit the resource, because this project started as my personal project, only me working on that. So you can see that I want a lot of things, but a lot of works. So how I made it. So if you start from scratch making Keystone, it will take I think it will take like 10 years or even more to have it mature. But I wanted to do this one in few months, not years of my life. So the idea is to stand on the giant shoulder at the first phase. After that, open source the project to get people involved and contributed. So the idea is that I rely on LVM. So LVM is an open source project on compiler, so you can build your own compiler based on LVM. LVM has huge community, very active, and it's backed by a lot of CPU vendors, because each CPU vendor, they want to build compiler for their CPU, right? So they back LVM to make LVM work for their CPU. So LVM is backed by AMD, Apple, Google, Intel, IBM, ARM, EMG Tech, NVIDIA, Qualcomm, Samsung, and a lot of other companies. It works on own kind of platforms. So LVM is a very nice project. LVM actually is a very complicated framework, but the most important thing is that I want is named machine code layer, one component inside of LVM. It's called also MC. So MC is like core layer for LVM, and a lot of things built around MC, like compiler, assembler, disassembler, debugger, just-in-time compiler, a lot of things built around MC. So the reason I chose LVM for Keystone is first one, because LVM is compiler, right? So MC support compiler inside, and compiler should support inline assembly, which means MC has many assemblers already inside, right? But note that MC, those compiler inside, those assembler inside MC is only built for LVM, but nothing else. You cannot directly use those assembler inside MC. And MC is very closely designed and implemented just for LVM, but nothing else. But the good thing is that MC components very actively developed and maintained by a lot of people in community. Another good thing is that MC is built is implemented in C++, so I can easily build Keystone on top of that. The final note is that LVM support many architectures, but not all of them support inline assembler. So only like 8 architectures now support inline assembler. So I can only build my Keystone for those 8 architectures. So yeah, I went for LVM because there's so many advantages. First one, LVM is built by professional developers from top companies. So the code quality is very high and it's very well tested. And the assembler inside LVM is maintained by top experts from each CPU vendors. For example, x86 is maintained by Intel. Who can do better than that? ARM64 is built by ARM and Apple. Can do that better? Hexagon maintained by Qualcomm, also the CPU vendor. MIPS maintained by IMG Tech, also CPU vendor. System Z by IBM, which is also CPU vendor. PowerPC and Spark maintained by a very active community. So there's nothing to worry about. And the new injection and bug fix are frequently added. So every time when the CPU vendor they add new injection, they quickly support LVM to support those instructions. So that's very nice. And if you fork LVM to build Keystone, bugs can be either reported to us or to LVM, and you can backport that. Okay, so we fork LVM to build Keystone. Is that easy? Which is not a lot of work. So we fork LVM to build Keystone, but there are many challenges. First one, as I said, MC is not just assembler, but it has many things inside. It includes disassembler, bitcode, instruction printer, linker, optimizer inside the MC for compilers. And the code is huge and it's mixed inside like spaghetti. So what I did is that I took a lot of time to read the source code MC, and I decided to keep only assembler code and remove everything else, which I do not really need, and I rewrite some components inside MC, but I keep the parser, the code emitter, the linker intact. The reason is that in the future, when LVM they update those components, I can easily catch up and update to follow them. But those less updated, those less used components, I can rewrite them. One more decision which I think is good is that unlike Capstone, because I fork LVM to build Capstone before, but Capstone was in pure C, no C++. But this time I decided I do not want C project, but I keep everything in C++, so it's easier to maintain, to update when LVM update. So Keystone was built in C++. So the good question is that you need to make a cut at MC to only take what I need out, but remove everything else. So the question is where to make the cut. If you cut too little, you end up having a lot redundant code that you do not really need. So framework will become bloated, right? But if you cut too much, you end up changing the code structure, which which make it very hard to maintain in the future. So yeah, this step took a lot of time to decide where to make the cut, and I think I came out with the optimal design for Keystone. I make the cut just enough. So second challenge, when you build LVM, you end up having a lot of separate components coming in separate libraries. So you have libraries for support architecture, is library for parser, you have library for linker, and so on. But what we want for Keystone is that we only need one single library for everything, right? So what I did is that I had to modify the link inside of VM to finally generate a single library for Keystone. So for example, for Linux or Unix, you have libkeystone.show or .dilib for share library, and you have libkeystone.a for static library. For Windows, you have keystone.dll for DLL or keystone.lib for static library. So only one library like that. The next issue is that assembler is not a final stage in the tool chain of compiler. So usually you compile code using assembler, and after that the output object will be sent to the linker, right? So you can see that the assembler doesn't know that if you do not declare some symbol, it doesn't know that symbol is missing. So for example, if you compile that Intel instruction there, but you do not declare var1, the assembler in LVM doesn't know that. It happily compiles that for you because it expects that var1 will come in the next phase in the linker. But Keystone is the assembler, and we expect that it compile and give us the final code. We do not have linker, right? So in this case, Keystone should report that var1 is missing. You do not declare that somewhere. So this code is invalid. So what I had to do is in this phase that in this step that I need to make some fixed subphase to detect and report the missing symbols, and I propagate the error back to the top level API KS ASMA. The next challenge is that LVM assembler is not aware of relative branch. For example, you compile that instruction BLX and some constant, it didn't happily give you the output on the right side. But actually the output is wrong because the final result should really depend on where you stay in the memory. If you stay closer to the target, the output should be different. If you stay further, the output should be different, right? Because it's branch, relative branch. So what I had to do here is that I designed the API, and this API allows you to specify the rest of the first instruction. And I changed the core of Keystone to retain the rest of each statement. And finally, I find and fix on the relative branch instruction. So the encoding is according to the current and the target areas. Yeah, so it took a lot of time. So the next thing is that LVM assembler is not really a framework, because when you give it some invalid input, it will crash and just exit with some reports like this one is not invalid instruction. So for example, if you compile that Intel instruction like this one X should be some constant, right? So this instruction is invalid. But when you compile this one using LVM assembler, it just say that this one is not invalid and inadequate, which is bad for, which is okay for LVM, but Keystone cannot do that because Keystone is framework, which is a part of the whole tool, right? It cannot crash, right? So what I had to do here is that I need to fix on the exit properly. I do not quit, but I file on the exit and I propagate the errors back to the high level API. So the exit can be in parser phase or on the co-emit phase or on the linker phase. There are many other issues with LVM. First one, LVM only support LVM syntax. So we want other syntax like nothing for x86, there's nothing. LVM doesn't support. There's no bindings. You have to build from scratch. And keep up with the upstream is very hard because LVM frequently updates the code. So what I had to do here is that I had to extend the x86 parser so I can support the new syntax like NASM is supported now. And initially I built Python binding myself from scratch. And after that, extra bindings came later, built by community. So we have 7 bindings totally now. And we had to frequently keep syncing with LVM to fix bugs, to add more change, more features. Yeah, so a lot of work. So here's the key flow, the flow for Keystone. Yeah, so we have the parser, we have code emitter, we have object writer, and given the input as assembly code, as the output you have the final encoding. Okay, so here's a quick summarize, compare Keystone with LVM. So we fork LVM to build Keystone, but Keystone goes a lot further, do a lot more, and do a lot better. So Keystone is a true framework. So we do not give up on bad input, and we allow tools built on top of Keystone. You cannot do that with LVM. It is aware of current composition, so we support relative branches properly for all the architectures. Keystone is much smaller in size and lighter in memory. So the size Keystone is like 10 times smaller than LVM because I remove a lot of things that you do not need inside Keystone. Keystone thread safe. You can build multiple thread programs on top of Keystone. Keystone is also more flexible. It supports NASM syntax for Intel CPU. Next good thing is that Keystone support many undocumented instructions of x86, which LVM doesn't support. I think LVM they do not care about undocumented instruction, but Keystone I want it to be very flexible and to build things that sometimes really wear some application in security communities. So yeah, we supported many undocumented Intel instruction. And finally, Keystone provide many bindings on top of that, and LVM doesn't. Okay, so that's how Keystone was designed, was implemented, and now you can see how to write application with Keystone. Okay, so the API, I think that I already came up with something very clean, very simple, very intuitive set of APIs for Keystone. The core is implemented in C++, but the API is provided in C. So you can write C code or C++, it's up to you. You have API to open or close Keystone instance. You have API to customize runtime engine. You can compile the input code. You have API to do memory management, like free allocated memory. And on top of the low-level API in C, we have a lot of bindings built on that. Okay, so here's one very simple example. Okay, so here's a demo, very simple demo in Python. You can see how easy and simple it is. So here, first one, I import Keystone, all right? I want to write Python code, so I need Keystone first. Next, I declare which instruction I want to compile. So you can see that I have 2 instructions here, and separated by this semicolon and next new line is up to you. Next, we set up the engine, and you can see that in this case I want assembler for Intel CPU 32-bit, and that's it. Next line, I compile the code here. So here's two instructions, right? And as the output, I have encoding, and cow is the number of statement I already compile, which is true, right? In this case. And finally, I print out the output. That's it. It's very simple. So you import the import keystone, you set up the engine, which architecture, which hardware mode, and you compile, and you get out. And as the output, you get the encoding. So I run this script. So here's output. We have two instruction and have two bytes encoding. So each instruction has one byte. So 65 is encoding for increase ECX. 74 is encoding for decrease DX. Yeah, so here's another C code which does actually the same thing, but it's also very simple. So here you see that I include keystone. I set up the engine, Intel CPU, 32-bit. I compile the code here. I specify the code. The first, the rest of the first instruction, which is 0, I get out encoding, the size of encoding, how many statements, and finally I print out. That's it. And here, after I compile the code, I freeze the memory, which contains the encoding. And finally, I close the engine. That's it. The set of API is very simple. Oh, it seems we have a lot of time. Right. Okay, so yeah, after I release Keystone, a lot of people already build many things on top of that, which I will show you later. Also myself, I build something. Okay, this tool that I want to introduce now is the tool named KeyPatch, which is open source IDA plugin, and you can get everything at the rest Keystone engine / KeyPatch. And KeyPatch is a tool for you to assemble or patch the binary when you analyze the binary inside IDA. And KeyPatch was co-developed with Nguyen from VN Security. So the reason behind this tool is that actually IDA has some built-in assembler, which means you can use assembler inside IDA to patch the binary, right? But why do you need KeyPatch? There are many reasons. Okay, so here is the IDA built-in assembler. So first of all, you want to change this one. Change push IBP instruction, right? You put the you stay here, and you choose patch program, built-in assembler of IDA, and it allows you to enter the new instruction. So you replace push IBP with something else. Now, let's see what happened. I change push IBP to push RSP. It's another valid instruction, right? And you can see that actually we analyzing the 64-bit Intel binary now. Now, you press OK. I expect that this push IBP will be changed to push ISP. But you see what happened? It said invalid operand, which means ISP is not a valid operand, which is wrong, right? It's because push ISP is a valid instruction. So that means the built-in assembler IDA is very buggy. It supports 32-bit, but not very well support 64-bit. And it has very few options for you to do. So now I try to fix that with a KeyPatch. Okay, so here you can right click and choose KeyPatch here. And here you can press hotkey Ctrl-Alt-K to open the dialog for patcher or key patch, or you choose one menu. It's up to you. Okay, so here's key patch, the patcher key patch. It tells you that this on Intel, of course. Syntax you can change here. The original assembler IDA do not have this flexibility, so you can choose the syntax here. It's up to you. It tells the rest, the original instruction, the size, encoding, and it allows you to enter the new instruction here. So now if you enter here, push ISP, you can see that it dynamically gives you the encoding when you type, right? And if the new instruction is shorter than the old instruction, I have one option to pad the extra byte no instruction. And there's one more option, so you can save the original instruction in the IDA command. So okay, patch here. And automatically the patcher move to the next instruction. And you can patch the next instruction. It's up to you. But I can cancel here. And you can see here, push IBP become push ISP. And here's a command. Key patch modify this from push IBP. So it's very convenient. It works, right? Some other features. You can choose a range of code. So like this 2 instruction, which is 1, 2, 3, 4, 5 bytes, right? And you can fill in with knob instruction. So we replace these two instructions with all the knob of code. So you choose from here, fill render. And you can enter like knob here, for example, right? And patch. So see here, 2 instructions become knob. So it knob out everything. Okay. And there's another tool inside key patch. Okay, you can choose one menu, pop-up menu. Oh, one more thing. You can undo the original built-in assembler in IDA doesn't allow you to undo what you patch, right? So I can undo here. So you see, you come back to the old instruction, right? And I can undo again. This one is push ISP, but originally it was push IBP, right? So I can undo one more and revert the first change to IBP. So you can change, you can do. One more tool inside key patch is the assembler, which is very handy. So you can see the patcher really change the binary, but this one doesn't. It allows you to do on cap compiling with assembly code. So for example, you enter knob. So for Intel, knob has encoding 90, right? You can change this one to ARM. So for ARM, knob is like 4 bytes like this. You can change the endian from little endian to big endian. You can see the encoding change as well. You can change this one to like hexagon. Or hexagon has some yeah, hexagon also has knob instruction. MIPS, yes, 0, 0, 0, 0. Spark, yeah, same, right? Yeah, something like that. Okay, there's one more things. I open another binary and show you why key patch is very powerful. Okay, this time I open some ARM binaries. Now, if I want to patch this instruction, okay, here, right? I choose the menu, the built-in assembler from IDA. No, patch program. Yeah, here's a built-in assembler from IDA. What happened? Sorry, this processor module doesn't support assembler. So ADA support nothing but Intel. So no ARM, no ARM64, no MIPS, no PowerPC, no Spark, nothing. But you can do that with KeyPatch because KeyPatch is built on top of Keystone, which support all those architectures. So here I right click this one, patcher. Okay. Now I can choose the original instruction is copy R7 register to R0, right? I can change this one to R8, for example. And you can see the new encode here. The original here, 0700A0E1 is a new one. 08, right? Okay, patch. Yeah, move to the next instruction. Cancel here. You can see it changed here. You already patched the binary. It's a new instruction. So yeah, KeyPatch support all those CPUs nicely. It has a lot more features, much more friendly. Okay, that's the first demo on Keystone, which is on KeyPatch, which is built on top of Keystone. The second demo, this one's also very interesting. Okay, so Ponypack is a toolset built by some guys from Netherlands, and this is a kind of toolkit for people playing CTF. A nice thing inside Ponypack is that they have some tool for you to write shellcode. So usually to mess with shellcode, you need to mess it to write shellcode. You need to mess with the low-level assembly, which is very complicated sometimes, right? Ponypack is nice because it allows you to write shellcode by describing high-level operation, and it writes a shellcode. It makes a shellcode for you. So inside, to use this one, you need to describe the high-level operation of shellcode, and after that, internally, Ponypack translate all those high-level operations to low-level assembly. And finally, it uses Keystone to compile assembly for different architectures. And that's why Ponypack can support shellcode for a lot of CPU. So here's the demo. Okay, I copy here. This is a Ponypack's a Python toolkit. So first one, you need to import the framework, Ponypack framework. So it's very flexible. And then you say that you want to generate a shellcode for Linux on CPU, Intel CPU, right? Linux x86 stack. And then you describe the shellcode in high-level language. And in this case, I want to write very simple shellcode, which does nothing but exit the process with zero as the output. So here is a shellcode for Linux CPU, Linux Intel on Intel, and if you run this one on Intel machine running Linux, you exit the process, right? Now, the good thing is that you can compile the same shellcode but for ARM. So here I declare this variable again, but this time I want to say that I want shellcode for Linux on ARM, not for Linux on Intel anymore. And again, I compile the same shellcode, which exits the process. And you can see different output. And this one is shellcode for ARM, not for Intel anymore. So you can see that internally, Ponypack use Keystone to compile the same shellcode for different CPU. Yeah, I think it's a very, very handy tool. You can find that useful for your CTF or whatever research. Okay, the next demo. Another tool named MetaMe, which is a metamorphic engine. So by concept, metamorphic engine is something came up from I think from malware virus community. So the idea is that you can change some instruction with something else that looks very different, but semantically they do the same thing, right? That's called that's the idea behind metamorphic. So by replacing some instruction with something looks totally different, but do the same thing, you do not change the semantics of the whole code, but the code looks very different, and you can bypass the signature matching antivirus, right? So here's on the screen, you can see that on the left side, the original instruction, they have like a lot of 90, a lot of knob of code, right? So you can use metame to change the original code on the left side to something on the right side, which has many instructions, which is not knob, but they do the same thing. They do not really do anything meaningful. So they do knob, but they look very different. And which means metame for you allow you to change your binary to something else differently, but still function is still the same. So yeah, I think this can be a very nice tool for you to experiment with bypassing antivirus. And internally metame support all kind binaries, Windows, Linux, macOS, and inside randomly replace some instruction with equivalence instruction, and metame use keystone inside to compile the equivalent instruction and assembly and write it back to the binary. Okay, so here is a demo. Okay, so I have one binary name LS, which I copy from my machine. So LS, what it does is just list all the file directories in your machine, and now I run metame on this binary. Input is LS, output is another one because I do not want to override ls.m, for example. So internally, when metame run, it file some instruction and it replace them with some equivalent instruction in assembly, and it uses keystone to compile and patch back. So you can see that here metame found like 15 instruction and it replaced with something else equivalently, but it's different syntactically. Okay, so here you have the new file name ls.m, and let's run this one. Yeah, it does the same thing with the original ls, but you can see that actually the binary are different. We have different binaries, but functionality, they do the same thing. Okay, there are a lot more applications built on Keystone now. You can find that from the website at the link there. Radar 2, they switch to Keystone as the default assembler now. Roper, another tool to build for you to build your exploitation. GEF, another GDB plugin. It uses Keystone inside. UserCon, another very nice tool to emulate the code. So you can emulate different binary on a different architecture, different platform. x64 debugger, they also switch from Intel XED to Keystone as a default assembler. There's some other tool for code injection for iOS, for another tool for deobfuscation. Yeah, so there are many different things you can see. Okay, so what's the status of Keystone? We released 2 versions so far, and Keystone was built on LVM version 3.9. And we plan to release the stable version 1.0 soon after we fix all the bugs, which is still many bugs, still some bugs now, not fixed yet. In the future, I want to add more API into Keystone, and I want to fix all the corner cases so you can handle graph input properly. You want to have more bindings from community, and yeah, you need to synchronize with the latest LVM version, because LVM release new version every 6 months. So we need to catch up with that. So Keystone can support new features introduced by LVM. But anyway, the future of Keystone is guaranteed because LVM actively maintains those assemblers, so we can easily catch up with them, and that works, but not too much. I think I can handle that, or community can help. So Keystone features guaranteed will be around. Okay, so here's a full diagram, full picture again. You can see that we have capstone to reverse from binary to assembly. You have keystone to compile back assembly to binary. So yeah, you can manipulate with the binary, and the binary can be sent to emulator to emulate it, so you can really understand what is happening inside the code. And all of them, capstone, keystone, emulator, are open source, multi-architectures, multi-platforms, multi-bindings, and they function independently, but together they make a complete set of frameworks. They complement each other very well. And so far already more than 200 applications built on top of these 3 frameworks, and we call them reverse engineering trilogy. And yeah, in the future, I still expect a lot more innovative works from reversing communities built on top of the trilogies. Okay, so here's my conclusion. Keystone is a next generation assembler which support many architectures. It support more in the future. It runs our own kind of platform. It has very clean and simple API. Implemented in C, but has many C and C++, but has many bindings on top of that. Trash safe, open source, in dual license, and future updates is busy. So there's no worry about the future for Keystone. And finally, we are seriously committed to Keystone project, and we want to make it the best assembly engine for community. By the way, I bring a lot of sticker for this trilogy, so anybody here want sticker, come to see me after my talk. Okay, so the on-card references, you get everything from the website, source code, documentation, binary package, tutorials, everything. KeyPatch is also open source as well. Okay, thank you so much for Apex to inspire me to build Keystone. And yeah, the name of Keystone I think is very nice. Thank you a lot for all the Indiegogo contributors to financially support the project, and thank you for all people who contributed code for Keystone. And thank you everybody.
Thank you very much.
Any questions? And don't forget stickers.
Yep. Maybe questions off stage. We're all looking forward to version 1.0, and any stickers, please feel free. But thank you very much, Nguyen. Thank you.
Thank you.
Yeah, we really
so much,
appreciate you coming back to stage.
I'm happy to be back to to be here for Hack in the Box.
Especially on the last minute, and to be talking about this framework. So we're really very excited. And good luck in the rollout of version 1.0.
Yeah, thank you so much. Yeah.
All right. Okay,
So
we're going to
take questions. I think you have 5 minutes.
Oh yes, there is a question. Okay.
I just wanted to say thank you as an active user of Capstone and hopefully now Keystone. And
oh,
they're
thank
beautiful.
you.
And
Yes,
thank you
good.
very much.
Yeah, good to see some user here.
Framework.
No questions. Thank you.
Okay, great. So we'll give us a few more minutes now, and then we'll set out for the final talk of today. All right. Thank you. Thank you.